So let us start today's lecture. Today I will try to prove that if XD is a metric space and G is any arbitrary open set in X, then G can be expressed as countable union of closed sets. Then G can be written as countable union of closed sets. Let us represent them by this, where An is closed set. So that means if we are going to take any arbitrary metric space and take any arbitrary open set from that metric space, then that open set can be written as countable union of closed sets. Okay, so let us write down the solution of this exercise. Let me write it like this. Let G be an open set in XD, in any arbitrary metric space. Let us define a map. Let us define a map F from let us define a map F from X cross X, X from X to R plus or R. So let G be an open set in the metric space. Let us define a function f from x to r plus by f of x equal to distance from x to G complement. Since G is open set, G complement is going to be closed set. Let us define it like this. Now, we know that distance between this point and this set G complement closed set is 0. When it is going to be 0? If this element is going to lie inside this, inside or on the boundary. So that means this is possible if and only if X belongs to G complement. G complement. So think geometrically a bit, then you can understand this proof. Think geometrically. That means distance between this point and this closed set is going to be 0 if and only if this element belongs to this closed set. This is what I have written here. So that means I can write, therefore I can write this distance is 0 if and only if x belongs to complement. That means let us define G to be, since G is open, G to be set of all elements x such that G is set of all elements, since G is open, G is set of all elements x such that distance from x to G complement. What is that distance going to be? Because we know that G complement is closed, so distance from x to G complement must be 0 because x belongs to closed G complement. Now G is open, so that means we have to write all those elements x whose distance from this complement is going to be positive. Is this setup okay? Because G complement is closed, so it is going to contain all its limit points, right? So since G is open, that means this is going to be disjoint from G complement. That means this open set must contain those elements which are not in G complement. So that means G is this. Okay. So now let us give it one more shape. I can write it like this: an equal to set of all elements x. Since this is positive, that means distance between them can be like this: 10 raised power 10 raised power minus 100 minus 1000. That means if this x belongs to G, that means the distance from this point to this closed set can be like this. That means this is going to be 0.00 something. Okay, this is almost 0 but positive. Almost 0 means that is going to be positive because distance is always going to be non-negative. That means an can be written like this: an is almost this, but distance from x to G complement is always going to be this, where we know that n belongs to n, where n belongs to n. That means distance is always going to be greater or equal to 1, greater or equal to 1 by 2, greater or equal to 1 by 3, and so on. So if we are going to approach infinity, then distance is always going to be greater or equal to 0. Since this is a sequence of sets, because I have involved n here. This is the reason I have replaced G by an, because I have involved n here. And my intention is this, because I am trying to approach this form. So now, therefore, can I write it like this? Since this means we have to involve f. So that means this set is going to be closed. Can I write it like this? an is equal to f inverse image of a set. That means inverse image of this set, closed 1 by n, because this distance is greater or equal to 1 by n. That means it will reach up to infinity. This is the reason I have written it like this. This is equal to this. This is just the inverse image of this because of this. Okay? Since we know that inverse image of a set is defined like this: set of all x's belongs to domain set such that f of x must belongs to this A. This is what I mean by inverse image of a set. So that means if an is equal to this, then I can write an is equal to this. Okay? Since this is closed set, and we know that distance is always going to be a continuous function. Metric is always a continuous function. That means f is continuous function. And we also know that this is a necessary and sufficient condition for a function to be continuous also. That is, inverse image of closed set is closed and inverse image of open set is open. So that means if an is equal to this, since this set is closed and f is already continuous because of this matrix presence, that means this is inverse image of a closed set. So this is going to be closed. Which implies an is closed. Which implies I can write G to be union of an, where n runs from 1 to infinity. Okay? That means I have written G as an arbitrary union of closed sets. G was open, and I have written G as an arbitrary union of closed sets because an is closed. I told you how this set an is closed. So that means any arbitrary open set in an arbitrary metric space can be written as a countable union of closed sets. Thank you.